We will now begin our discussion of how to graph trigonometric functions. In graphing trigonometric functions, it'll be useful to remember that trigonometric functions are periodic. So this will be unlike most of the functions you've seen up to this point. So here is the graph of y equals sine of x. And what you'll notice is that this function goes back and forth. So there is what we call an oscillation of this function around a line which is our x-axis. So one of the other things that you'll notice is that this function, as it oscillates, will repeat. So if we, for example, we start at a crest and we look at the next crest, this will complete one full cycle. So there is one full cycle. Now we don't have to start there and end there. We could start at the origin and we can go to 2 pi and there is one full cycle. The next part of our curve will repeat that same cycle. So those two are exactly the same. So how long does it take for you to complete one cycle? If you remember, in a previous video we discussed the period of the sine function is 2 pi. So we use the variable capital T to denote the period. So the period is 2 pi. Now our line of oscillation here is our x-axis, y equals 0. The distance that we deviate from that line of oscillation is called the amplitude. That amplitude in this case is 1. So let's look also at the domain and the range of this sine function. The domain, well, this goes forever to the left and forever to the right. So the domain is negative pi to pi, which we've already seen in previous video. And the range of our sine function we can also see goes from negative 1 to 1. So as before, whenever we went to graph functions, we looked at a parent function, then we applied transformations on that parent function. So here are some key points that we have on our parent function. So the sine of 0 is 0, the sine of pi over 2 is 1, the sine of pi is 0, and so on and so forth. So we can see those on our curve if we mark our x-axis. And as we graph our trigonometric functions, one thing to remember is that our independent variable is always going to be measured in radians. And then our output will be corresponding to a ratio. And as in our previous slide, we marked out that the distance from our line of oscillation is our amplitude. So here our line of oscillation is y equals 0. And the distance that we deviate from that line of oscillation is the amplitude. And so the amplitude, we call it the absolute value of A. That is 1. The reason why we call it the absolute value of A has to do with the form of our trigonometric function in a generalized format. The period here we've already seen is 2 pi, and we've marked out that in the previous slide, and we've told you that t equals our period. So we can use our transformations to change how this graph looks. So whether it be a shift horizontally, a shift vertically, or our stretches or compressions vertically or horizontally, or reflections, so on and so forth. So as we look at y equals sine of 3x, notice that this 3 is a change on the input and it's a multiplication. So this will correspond to a horizontal compression by a factor of 3. Now, a horizontal compression would mean that we're changing our period. So the period of the original function is 2 pi, and now we are compressing that by a factor of 3, so our new period is 2 pi over 3. So let's look at our table of values that we originally had. We had x and we had y equals sine of x. And we'll see how this table changes for our function. So we had 0, pi over 2, pi, 3 pi over 2, and 2 pi. Sine function, our parent function, starts at the line of oscillation and increases and goes back and down and back. So what's this mean for our function, y equals sine of 3x? If we are horizontally compressing this, then that means that our x values will shrink by a factor of 3. One of the easy ways to do this is, notice there was no movement left or right, so our x value starts at 0 still, and then we need to know how much we move between these x values. So our original increment was pi over 2. How will we obtain our new increment for our x values? So our increment is easily determined by taking the period and dividing it by 4. This is taking our whole period and dividing it into quadrants. So 2 pi over 3 divided by 4 gives us pi over 6. So we will move pi over 6 between each of these. So 0 plus pi over 6 is pi over 6. Now I'm going to add pi over 6 more to that. So one thing that you'll be aware of is, let's keep the denominator as 6 until we're ready to finally simplify things. So pi over 6 plus pi over 6 is 2 pi over 6. And then 3 pi over 6. And then 4 pi over 6. Now the outputs of this function will be the same as the outputs for the original function, our parent function, but with these inputs having changed. So 0 will still go to 0. But instead of pi over 2 going to 1, pi over 6 will go to 1, and so on and so forth. So now let's go ahead and mark out this graph. So let's just start with our horizontal axis. In this case, our horizontal axis corresponds to x. So let's start off with a tick mark, and then I will increment until I know that I will have completed one period. Every period consists of 5 key values. So this is the beginning of our period, this is the middle, and this is the end. So this ending of the period is the beginning of a new period. So I will need 4 more key values after this one in order to complete 2 full periods. Now let's work on ticking off our x-axis. So we start off with 0, and then we have pi over 6 is our increment, so I'll add pi over 6. There's the end of our first period and the beginning of our next period. Now, we'll go back and we will simplify the fractions that we can simplify. So 2 pi over 6 is the same thing as pi over 3. 3 pi over 6 is pi over 2. On down the line. So 2 pi over 3, 6 pi over 6 became pi, and 8 pi over 6 is 4 pi over 3. Now, we know that when x equals 0, we have our y-axis. And the maximum value of our tick mark on our y-axis is based upon two things. Our line of oscillation, which we had no vertical translation, so our line of oscillation is y equals 0. Our amplitude for this function is 1 because there is no vertical stretching. So we'll go up 1 and down 1 from that line of oscillation. So this is our y-axis. And this is our x-axis. And so therefore, let's go ahead and mark out our key values. So according to our table, we had 0, 0, pi over 6, 1, and so on and so forth. And there is the end of our first period. So we'll make a nice smooth curve. And then we will repeat. Extending past our last points to ensure that we know that this function continues in a like manner in either direction. And so there is our function. So let's mark out the key things that we were supposed to say. The amplitude is 1. The period we said was 2 pi over 3. The domain of a sine function is negative infinity to infinity, and the range of this function is negative 1 to 1. We can see that graphically. Now, just to highlight some things, notice that we do have more than one cycle. We have our first cycle, and then we have our second cycle. And so we've completed the directions. We've graphed the function showing at least 2 cycles. We've determined the amplitude, the period, the domain, and the range of this function. So now as we look at y equals 2 sine of x, this 2 corresponds to a vertical stretch because it's affecting the output of our sine function. So if you think about what that would affect it affect the period? The period is how long horizontally it will take for you to complete one cycle. But in this case, I have a vertical stretch. So that will correspond to a change in the amplitude of our function. So here, my amplitude is going to now be 2. So let's look at what our original parent function was. These were our original values. But now we have our table changes with the outputs, unlike the previous example. So let's maybe remember our period here has not changed. It's 2 pi. Our increment, so that's the values between each x value in our table, is the period divided by 4. So 2 pi over 4 is still pi over 2. There was no horizontal shift, so we still start at 0. And now we increment by a pi over 2. So 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. But now, each y value is doubling what we had in our parent function. So instead of 0, we will now have 0, but 1 will correspond to a 2 in our adjusted function, our transformed function. Likewise, down the line. So let's go ahead and mark out our x-axis and look at graphing this function. So again, we start off, I'm going to put 9 values. So you might think I had 5 key points in my first period, won't I have 5 key points in my second period? So 5 plus 5 is 10. Why do I have 9? Well, remember that between periods, the ending of one period is the beginning of another. So the 5th point of my first cycle is the first point of my next cycle. So it's 5, plus then I need another 4. So here we go. I start off with 0, and then my increment here is pi over 2. So 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, simplifies to 2 pi, 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2. Now let's find our y-axis. Our y-axis is if x equals 0. So here is our y-axis. That makes this our x-axis. And in this case, our line of oscillation, there was no vertical translation, so it is still y equals 0. And our amplitude tells us how much we deviate from that line of oscillation. So we are stretching this out by a factor of 2. So we still start at 0, 0 on the line of oscillation, but then for pi over 2, we move upward. We're still increasing off that original point, but this time instead of just going up by 1, we're going up by 2, and then back, and then down by a factor of 2, and back. So there is one period. No sharp turns on our sine function. And then let's continue on with the pattern. And there is our graph. So let's mark out, make sure that we finish what we began with. We said that our amplitude was 2, the period was 2 pi, the domain here is still negative infinity to infinity, and the range, in this case, we start at the lowest value is negative 2, and the highest output is positive 2. So now let's look at a more complicated function for which there are several things going on. So let's start with the inputs. We have a factor of 3 multiplying our x, and so that means that we have a horizontal compression. And so that's going to affect the period. The period is now 2 pi is going to be divided by 3, which, if we want to go ahead and mark out our increment while we're at it, the increment is the period divided by 4. So we have 2 pi divided by 3 divided by 4, which is pi over 6. So now we have two things going on with this coefficient of sine. We have the negative, which is a reflection about the x-axis, and the 1/2 is a vertical compression. Now, why do we say the amplitude is the absolute value of A? Well, if we were to write this out, A equals negative 1/2. So therefore, the amplitude is positive 1/2. So now, we also have this 1, which is a shift up of 1 unit. This means that our line of oscillation is now y equals 1. So let's look now at creating our tables. So we have our original parent function, and it's okay if you're able to eventually wean yourself off of writing out these two tables. I would hope that we could do that. But as we're gaining our bearings, there's nothing wrong with doing this. It's always okay to show more work, as long as we always end up with the correct answer. So we have 0, pi over 2, pi, 3 pi over 2, and 2 pi. 0. And then with our original sine function, we go up, and then back, and down, and back. So what is it, what's occurring with our function? So we start off, there is no horizontal translation, so we are starting with x equals 0. Our increment was pi over 6, so I will add pi over 6 to each one of these. So pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. So we have now shifted this function upward. So our line of oscillation is now y equals 1 instead of y equals 0. So every time we had 0 for an output, we'll now have 1. Now, this function has been reflected, which means that instead of increasing from our line of oscillation, we are now going to go down from our line of oscillation. And how much do we go down? Well, the distance we deviate from our line of oscillation is our amplitude. So instead of going from 0 to 1, as in our original function, we're going to go from our line of oscillation down by our amplitude. So we'll go down by 1/2. So going down by 1/2 from 1 lands me at 1/2. Then I'm going to go back up to my line of oscillation, that's to 1, and then I'm going to go up 1/2, which is 1.5, or 3/2, and I'm going to go back to my line of oscillation, which is 1. So now let's put this on our graph. So here is our horizontal axis with our 9 tick marks. So 0, pi over 6, and that's increment in pi over 6's, remember. So 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6. And then our vertical axis, our y-axis, is whenever x equals 0. And our line of oscillation was when y equals 1, and our amplitude was 1/2. So if that's y equals 1, then our line of oscillation is this horizontal line. And we start on the line of oscillation, and this time we descend from our line of oscillation because of that negative in front of the sine function. And so therefore, we're down to 1/2, and then we're to our line of oscillation, and up and back. And then we continue the pattern. And so, let's take inventory of the things that we have found. The amplitude was 1/2. The period was 2 pi over 3. The domain is negative infinity to infinity. And the range, notice the lowest value is 1/2. The highest value we attain is 3/2. So the range is 1/2 to 3/2. So now let's look at our final example for our sine functions. To look at this example, let's first rewrite the sine function as the sine of, and I'm going to factor out a 2 in the argument, so it'll be 2 times x minus pi over 2. That way we can clearly see the transformations. But notice, this 2 must stay in the argument. It cannot come outside of the sine function. The sine function does not operate so that you can take a factor out of it. It must stay in. So we have two things going on here. We have a 2, and then we have this pi over 2. This pi over 2 is a shift to the right, pi over 2 units. The 2 is a horizontal compression, which will affect the period. So, what is the period? The period is originally 2 pi, but will be divided by 2. So the period is pi. The increment is the period divided by 4, so pi over 4. Now, let's look at our table. And this is where we have something that we have not yet happened. The shift to the right of pi over 2 units, that is called the phase shift. So the phase shift is easily found by just taking the argument, 2x minus pi, and setting it equal to 0. So if that happens, we have x equals pi over 2. That's the phase shift. So instead of starting at 0, as we have done in the previous examples, we're starting at pi over 2. And then we are going to increment by pi over 4. So it might be beneficial to think of pi over 2 as 2 pi over 4. since that would have the same denominator. So 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4. Notice the amplitude has not changed because there is no vertical stretching. The line of oscillation is still the x-axis because there is no vertical translation. So our outputs should correspond to the typical sine pattern. So start on the line of oscillation, go up by the amplitude, back to the line of oscillation, down by the amplitude, back to the line of oscillation. Now let's go ahead and put this into our graph. So let's go ahead and mark off our axis. So we have pi over 2. Then we have an increment of pi over 4. So 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, 9 pi over 4, 10 pi over 4. Now as we look at this, you'll notice that there is no x equals 0 on our horizontal axis. So we need to back up and include our tick marks for the left of pi over 2. So if we increment to the left 2 units, that should be enough to capture x equals 0. So 2 pi over 4 is pi over 2. So 2 pi over 4 decreased by pi over 4 increment is 1 pi over 4. And then increment to the left one more time, and that gives you 0, which would then be our y-axis. So let's go ahead and tick off our y-axis. We know that our line of oscillation is still y equals 0. Our amplitude is still 1. So we'll go from our line of oscillation up 1 unit and down 1 unit. And then we'll put in our values. So we started, our phase shift was pi over 2. So that will determine our initial value. And so that pi over 2, since we're with the sine function, begins on our line of oscillation. So pi over 2 gets assigned to 0. And then we increase, and then back to our line of oscillation, and we go down and back. And so there's one full period. And we just continue the pattern. And if we wanted to back up, we could do so as well. So here we go. And we connect with nice smooth curves. And now let's analyze our function. We've already said that the amplitude is 1. The period we've already stated to be 2 pi over 2, which is pi units. We've said that the domain of our sine functions are negative infinity to infinity. And here the range was not altered, so it's going to go from -1 to 1.